What's up, Zoomers? Today we're going to take all of linear algebra, this scary math thing from your textbook, and turn it into something your brain actually likes. In the next 10 minutes, you'll finally understand vectors, matrices, eigenvalues, eigenvectors, and why every computer on Earth is obsessed with them. No stress, no heavy formulas, just vibes, visuals, and simple logic. Let's cook. So, what even is linear algebra? Forget the scary name. Linear algebra is just the math of arrows and how we transform them. These arrows are called vectors. The machines that transform them are called matrices. Everything else is just fancy ways of saying, take this arrow, do something to it, and see what happens. That's it. That's the core. Let's start with vectors. A vector is basically an arrow. It points somewhere and has a length. Imagine a flat 2D grid, like a graph from school. You put an arrow starting at the center, the origin, and pointing somewhere. That arrow might land at the point 3, 2. So we say the vector is v equals 3, 2. That just means move 3 steps to the right, move 2 steps up. The numbers you see, those coordinates, are just instructions for how to walk from the center to the tip of the arrow. So a vector is not just a point, it's a direction, plus distance. You can think of it as go here from the starting point. What can we actually do with vectors? Two main things. Add vectors. You put the tail of one arrow at the head of another. The result is a new arrow from the start of the first to the end of the second. In numbers, you just add coordinates. 3, 2, plus 1, 4, 4, 6. Multiply by a number, a scalar. If you multiply a vector by 2, you make it twice as long. 3, 2, x2 times 6, 4. Multiply by 0.5, it shrinks. That's already most of what you do in vector land. Combine directions and stretch them. If you want to solve linear algebra right in your browser, I recommend installing the AI-powered screenshot solver extension in your desktop browser. Just take a screenshot and get an instant answer. It has two modes, step-by-step mode and quick answer mode, for when you're short on time. It doesn't just solve math, it can help with any school or college subject. The link to the extension is in the description. Now, big smart phrase, vector space. A vector space is just a world where you can add vectors and multiply them by numbers and everything still makes sense. If you can add two vectors and still get a valid vector and multiply any vector by any real number and still stay in the system, you're in a vector space. So 2D arrows, that's a vector space. 3D arrows, also a vector space. Even crazy abstract things like lists of numbers, functions, etc. can be vector spaces, as long as they play by the rules. You don't need to memorize formal definitions. Just remember, vector space, all the vectors that live together and follow the same rules. Now we get to basis, one of the most important words in linear algebra. A basis is just a small set of vectors that can build every other vector in the space. Imagine you have two simple arrows in 2D, e sub 1 equals 1, 0. One step to the right, e sub 2 equals 0, 1. One step up. With just these two arrows, you can build any vector in the plane. For example, 3, 2, sure 3 times e sub 1 plus 2 times e sub 2. So the basis gives you the building blocks, the coordinates tell you how many of each block you need. You can think of basis vectors as the axis of your world. Change the basis, you change how you describe everything. You don't have to use 1, 0 and 0.1 as your basis. You can choose any two non-parallel vectors. For example, b sub 1 equals 1, 1. b sub 2 equals 1 minus 1. These two can also build any vector in the plane. You just get different coordinates, same reality, different language. It's like switching from meters to feet. Things don't move, only the numbers change. Linear algebra is full of this idea. Same object, different coordinate system. Now the main character enters, matrix. A matrix is just a grid of numbers, like A equals a 2 by 2 matrix with 1, 2 in the first row and 3, 4 in the second row. Instead of being scared of it, think. A matrix is a machine that eats vectors and spits out new vectors. You give it a vector v, it gives you a new vector a times v. Geometrically, a matrix can rotate the space, stretch it, flip it, squish it, or do combinations of these. Each column of the matrix shows where your basis vectors go after the transformation. For example, if the first column is 2, 0, and the second is 0, 1, then E sub 1 gets doubled, E sub 2 stays the same. So the matrix is just saying, here's what I do to the basic directions. Everything else follows. When you compute a times v, you're basically doing v sub 1 times first column plus v sub 2 times second column. So if v equals 3, 2, a equals bracket col sub 1, col sub 2 bracket, then a times o equals 3 times col sub 1 plus 2 times col sub 2. It's just mixing the columns according to the coordinates of v. So you can think, multiply matrix by vector. Blend these basis vectors using the vector as a recipe. What about multiplying matrices? A times b means first do b, then do a. So matrix multiplication is just combining transformations. Rotate, then stretch, then rotate project, then flip. The order matters. Doing a then b is usually not the same as b then a. So matrix multiplication is about one machine after another. Now, determinant. The determinant of a matrix tells you how much the matrix scales areas in 2D or volumes in 3D. Does it squish everything into a lower dimension? If daddy of A equals 2, area doubles. If daddy of A equals 0.5, area gets cut in half. If daddy of A equals 0, your whole space gets flattened into a line or a plane. So when that equals 0, you lose information. You can't undo the transformation. The machine threw away data. So, determinant. How much stretching? Plus, can we reverse this? Next word, rank. The rank of a matrix tells you how many independent directions survive after the transformation. Full rank, no directions are completely killed. Lower rank, some directions get mapped to 0. Imagine you had a 3D space, but the matrix flattens it onto a 2D plane. Then the rank is 2. So, rank. How many dimensions are still meaningful after we apply this matrix? This shows up everywhere in solving systems of linear equations, in data compression and machine learning. Now the mysterious duo, eigenvectors and eigenvalues. A vector is an eigenvector of a matrix if, when the matrix acts on it, the vector doesn't change direction, only its length changes. Mathematically, a times v equals lambda times v, where v is the eigenvector lambda. Lambda is the eigenvalue geometrically. The matrix might twist and distort the whole space, but some special directions just get stretched or squished. Those special directions are eigenvectors. The amount they're stretched by is the eigenvalue. You can think of them as the natural directions of the transformation. If you understand the eigenvectors and eigenvalues of a matrix, you pretty much understand what the matrix does to the entire space. Sometimes a matrix can be diagonalized. That means there's a special basis in which the matrix becomes super simple, just a diagonal of eigenvalues. Instead of a messy mix, it turns into scale this direction by lambda sub 1, scale that direction by lambda sub 2, scale the next by lambda sub 3. This is insanely useful for solving differential equations, analyzing stability in systems, understanding Markov chains, machine learning algorithms, graphics, physics simulations, and more. So to recap, vectors are arrows, vector spaces are worlds where arrows live and combine, bases are the building blocks of those worlds, matrices are machines that transform vectors. Determinants tell you how much they stretch or squash space. Rank tells you how many dimensions survive. Eigenvectors and eigenvalues reveal the secret natural directions of a transformation. And that, Zoomers, is linear algebra. Not as a pile of symbols, but as a language for how things move, stretch, rotate, and change. If your teacher made it way more confusing than this, send them this video. We're done.